Welcome to DAR Tutors. Today, we'll be exploring the fundamental concepts of ideal and real gases, a crucial topic in the IB Chemistry higher level curriculum. By the end of this session, our learning objectives are as follows. First, you will be able to describe the key assumptions of the ideal gas model. Second, you will learn to solve problems using the gas laws and the ideal gas equation. And third, you will be able to explain the limitations of the ideal gas model and why real gases deviate from ideal behavior. Let's begin by defining pressure, a key property of gases. Pressure is defined as the force exerted per unit of area. The SI unit for pressure is the Pascal. 1 Pascal is equivalent to 1 Newton per square meter. A common misconception is that gas pressure is caused by molecules colliding with each other. This is incorrect. Pressure is caused by gas molecules colliding with the walls of the container. These collisions are perfectly elastic, meaning no kinetic energy is lost. Now, let's introduce the concept of an ideal gas, which is a theoretical model used to simplify the study of gas behavior. The ideal gas model makes two fundamental assumptions. First, the total volume occupied by the gas molecules themselves is negligible compared to the total volume of the container. In other words, the molecules are considered as points with no volume. Second, there are no intermolecular forces of attraction or repulsion between the gas molecules. The molecules act in a completely independent manner. These assumptions are the foundation of the kinetic molecular theory of gases. Let's visualize them. Here we see an ideal gas. The particles are widely spaced, indicating their negligible volume, and there are no forces shown between them. This model also provides a crucial link between temperature and particle energy. The mean kinetic energy of the gas particles is directly proportional to the absolute temperature. This means as temperature increases, the particles move faster, and as temperature decreases, they slow down. It's important to note that the average kinetic energy depends only on temperature. At a given temperature, particles of lower molar mass will move more quickly on average than particles of higher molar mass to maintain the same average kinetic energy. Another important concept is absolute zero, which is 0 Kelvin. This is the theoretical lowest temperature possible, where all atomic motion stops and there is no internal energy. Let's now consider how this ideal gas model applies to real gases and where its limitations lie. This will address our third learning objective. No real gas behaves exactly as an ideal gas. Real gases deviate from ideal behavior, especially under certain conditions. A real gas is a gas that does not obey the ideal gas equation. A common misconception is that gases are divided into real gases and ideal gases. All gases are real gases. The key is that real gases can approach ideal behavior under specific conditions: low pressure and high temperature. Under these conditions, the particles are far apart and moving very fast, so the assumptions of the ideal gas model are reasonably true. However, let's see what happens at high pressure and low temperature. At high pressures, the volume of the container becomes much smaller. This means the total volume occupied by the gas molecules themselves is no longer negligible. The space available for the molecules to move is less than the container volume. At low temperatures, the particles move much slower. This gives the intermolecular forces more time to interact and become more significant. These attractions pull the particles closer together, reducing the force of their collisions with the container walls. In essence, at low temperatures and high pressures, the two main assumptions of the ideal gas model break down. The extent to which a real gas deviates from ideal behavior depends on the strength of its intermolecular forces, which in turn depends on its polarity and size. Deviation is greatest for molecules with strong intermolecular forces, such as polar molecules and large molecules. Deviation is smallest for small nonpolar molecules like the noble gases, which only have weak London dispersion forces. Let's work through an example. Consider the gases: helium, neon, oxygen, water, ammonia, and ethane. We need to list them in order of increasing deviation from ideal gas behavior. We will order them from weakest to strongest intermolecular forces. The weakest are the noble gases. Helium is the smallest noble gas, so it has the weakest London dispersion forces. Next is neon. Next are the small nonpolar diatomics like oxygen. Ethane, C2H6, is a larger nonpolar molecule, so it has stronger London dispersion forces than oxygen. Ammonia, NH3, is a polar molecule and can form hydrogen bonds, which are much stronger. Finally, water, H2O, can form more hydrogen bonds per molecule than ammonia, making its intermolecular forces the strongest on this list. Therefore, the final order is helium, neon, oxygen, ethane, ammonia, and water, from least to most deviation from ideal behavior. We can describe a sample of gas using 4 interdependent variables: pressure, P, and volume, V, temperature, T, and the amount in moles, on. Let's first look at the 4 classical gas laws, each describing the relationship between 2 of these variables while keeping the other 2 constant. Boyle's law states that for a fixed amount of gas at constant temperature, pressure is inversely proportional to volume. As one increases, the other decreases. Next, let's explore Charles's law. Charles's law states that for a fixed amount of gas at constant pressure, volume is directly proportional to the absolute temperature. Gay-Lussac's law, or the pressure law, tells us that for a fixed amount of gas at constant volume, pressure is directly proportional to the absolute temperature. Finally, Avogadro's law states that for a fixed pressure and temperature, volume is directly proportional to the amount of gas in moles. More gas particles mean more volume. A critical point for all gas law calculations is that temperature must always be expressed in the Kelvin scale. Do not use Celsius. To convert, simply add 273.15 to the Celsius temperature. The ideal gas equation combines all 4 gas laws into one comprehensive formula. It's the most powerful tool for solving problems involving ideal gases. The ideal gas equation is PV equals nRT. Here, P is pressure in pascals, V is volume in cubic meters, N is the amount of gas in moles, and T is the temperature in Kelvin. It's the gas constant, with a value of 8.31 joules per Kelvin per mole. This value depends on the units used for P and V. This single equation can be rearranged to solve for any of the variables, making it incredibly versatile. Before we work through some examples, let's review the standard conditions often mentioned in gas problems. There are 2 main sets of standard conditions you need to be aware of: STP and SATP. STP, or standard temperature and pressure, is defined as 0 degrees Celsius or 273.15 Kelvin and a pressure of 100 kilopascals. At STP, a very useful constant emerges, which simplifies many calculations. At STP, the molar volume of an ideal gas is 22.7 cubic decimeters. This means 1 mole of any ideal gas will occupy 22.7 cubic decimeters of space. We can convert between volume and moles using this value. The other set of standard conditions is SATP, or standard ambient temperature and pressure. This is 25 degrees Celsius or 298.5 Kelvin and a pressure of 100 kilopascals. At these conditions, the molar volume is slightly larger at 24.8 cubic decimeters per mole. It's crucial to pay close attention to the conditions specified in a problem to ensure you use the correct temperature and molar volume. A common mistake is to confuse STP and SATP. Let's work through some examples to solidify our understanding of these concepts. We'll start with molar volume calculations. This problem asks us to calculate the volume of 1.35 moles of oxygen at STP. Since the question specifies STP, we can use the molar volume constant of 22.7 cubic decimeters per mole. To find the total volume, we multiply the number of moles by the molar volume. Plugging in our values, we get 1.35 moles times 22.7 cubic decimeters per mole, which gives us 30.6 cubic decimeters. The moles units cancel out, leaving us with the correct unit for volume. Let's try another one, working in the opposite direction. This time, we're given a volume and asked to find the number of moles. Again, the conditions are STP. First, we need to ensure our units are consistent. The molar volume is in cubic decimeters, so we should convert the given volume from cubic centimeters to cubic decimeters. Since 1 decimeter is 10 centimeters, 1 cubic decimeter is 1,000 cubic centimeters. So 175 cubic centimeters divided by 1,000 gives us 0.1175 cubic decimeters. Now we can use the molar volume constant. To find the number of moles, we divide the volume by the molar volume. 0.175 cubic decimeters divided by 22.7 cubic decimeters per mole gives us approximately 0.0771 moles of hydrogen. These examples demonstrate how the molar volume concept at STP simplifies calculations. Now let's tackle problems where we use the combined gas law. This law is useful when the amount of gas is constant, but all three variables P, V, and T are changing. The combined gas law states that P1V1 over T1 equals P2V2 over T2. This allows us to find a new state of the gas given an initial state. Remember our top tip: temperature must always be in Kelvin. Here's an example. A gas sample at 7 degrees Celsius and 100 kilopascals has a volume of 4.5 cubic decimeters. What is its volume at 350 Kelvin and 100 kilopascals? Let's identify our initial and final states. The initial state has a pressure of 100 kPa, a volume of 4.5 dm3, and a temperature of 300 K. The final state has a temperature of 350 K and a pressure of 100 kPa. We need to find the final volume, V2. Notice that the pressure is constant. This simplifies the combined gas law to Charles's law. Since P1 equals P2, we can cancel them from the equation, leaving us with V1 over T1 equals V2 over T2. To solve for V2, we rearrange the equation. V2 equals V1 times T2 divided by T1. Plugging in our values, V2 is 4.50 cubic decimeters times 350 Kelvin, all divided by 300 Kelvin. This gives us a final volume of 5.25 cubic decimeters. The ideal gas equation can be rearranged to derive formulas for other useful quantities like molar mass, density, and concentration. Let's first derive the formula for molar mass, M. We know that the number of moles, N, is the mass, M, divided by the molar mass, M. So we can substitute M over M for N in the ideal gas equation. Rearranging this to solve for M gives us the formula for molar mass. M equals MRT divided by PV. Now let's find the formula for density, ER. Density is mass over volume, or M over V. From our molar mass formula, we can see a mass over volume term. Rearranging for density, we get RAP+CU equals PM divided by RT. This is a very useful formula to remember. Let's apply these new formulas. Here is a worked example to calculate molar mass from experimental data. The problem states that 12.64 grams of a gas occupies 4 cubic decimeters at STP. We need to find its molar mass. First, identify the given variables. We have a mass of 12.64 grams, a temperature of 273 Kelvin, a volume of 4 cubic decimeters, and a pressure of 101,325 pascals. We use the gas constant R, which is 8.31 joules per Kelvin mole. A crucial step here is unit conversion. Remember, the value of R we're using is for pascals and cubic meters, so we must convert our volume from cubic decimeters to cubic meters. There are 1,000 cubic decimeters in a cubic meter, so 4,000 dm3 becomes 0.04 mers. Using our formula M equals MRT over PV, we can substitute in all the values. Solving this calculation gives us a molar mass of 71.0 grams per mole. By identifying the variables, converting units, and applying the correct formula, we can solve for the molar mass. Finally, let's explore gas mixtures and Dalton's law of partial pressures. This is an important topic, particularly for understanding experiments where gas is collected over water. Dalton's law states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual constituent gases. The partial pressure of a gas is the pressure it would exert if it were the only gas present in the container. The law works best when the gases do not react and behave ideally. A common application is collecting a gas over water. The collected gas will not be pure. It will be saturated with water vapor. The pressure measured in the container will be the sum of the partial pressure of the gas we collected and the partial pressure of the water vapor, which is also known as the vapor pressure of water. Let's work through an example of a gas mixture problem. Imagine we have two separate gases, nitrogen and argon, which are then mixed into a single smaller container at the same constant temperature. First, we calculate the partial pressure of nitrogen. It was at 400 kilopascals in 4.0 cubic decimeters and is now in 2.0 cubic decimeters. Using Boyle's law, P1V1 equals P2V2, we find the new partial pressure, P2 of nitrogen, is 800 kilopascals. Next, we do the same for argon. It was at 200 kilopascals in 1.0 cubic decimeter and is now in the 2.0 cubic decimeter container. The partial pressure of argon, P2, is 100 kilopascals. Finally, to find the total pressure, we apply Dalton's law. We add the partial pressures of nitrogen and argon. Let's put everything we've learned together with a more complex problem. This problem also involves stoichiometry, connecting the gas laws to our earlier chemistry studies. The problem asks for the mass of lithium hydroxide needed to absorb all the carbon dioxide produced by a 70-kilogram astronaut in 10 days. This is a multi-step problem. Our strategy will be to first find the total volume of CO2, then the moles of CO2, and finally the mass of LiOH. First, let's find the volume of oxygen used by the astronaut each day. The volume of air breathed in one day is 14,400 liters. Since air is 21% oxygen, the volume of oxygen used is 324 liters. Assuming an astronaut produces roughly the same volume of CO2 as O2 consumed, the daily volume of CO2 produced is also 324 liters. So over 10 days, the total volume of CO2 produced is 30,240 liters, which is 30.24 cubic meters. Next, we convert this volume to moles using the ideal gas law, PV equals nRT. First, we convert pressure to pascals and temperature to Kelvin. Plugging in the values, we find that the astronaut produces approximately 1230 moles of CO2. Finally, we use the stoichiometry of the reaction. The equation tells us that 2 moles of LiOH are needed for every 1 mole of CO2. Therefore, 30 moles of CO2 requires 2460 moles of LiOH. Multiplying by the molar mass of LiOH, which is 23.95 grams per mole, gives us a mass of 58.9 kilograms. So, nearly 59 kilograms of lithium hydroxide are needed. Let's quickly recap what we've covered today. We started with the assumptions of the ideal gas model, which simplifies gas behavior by neglecting particle volume and intermolecular forces. We then saw that real gases deviate from this ideal model at high pressures and low temperatures, conditions where those assumptions break down. We reviewed the 4 gas laws, the combined gas law, and the fundamental ideal gas equation, PV equals nRT. We also learned how to use these to calculate molar mass and partial pressures, and the importance of using Kelvin for temperature. Now, it's time to test your understanding with some IB-style practice questions. Take your time, show your work, and then check your solutions. Good luck. Practice question 1. A gas occupies 125 cm3 at 0.85 atm and 25 deg C. What is its volume at standard ambient temperature and pressure, SATP? Pause the video here and try to solve this on your own. Remember to think about what the question is asking for. Welcome back. Let's walk through the solution to practice question 1. The problem involves a gas changing conditions, so we'll use the combined gas law. We first need to define SATP. Standard ambient temperature and pressure is 298.15 Kelvin and 100 kilopascals. Our initial temperature of 25 degrees C is 298.55 Kelvin. Our initial pressure of 0.85 atm is 86.175 kilopascals. We can see that the temperature is constant, which simplifies our equation. The final volume V2 is equal to V1 times P1 over P2. Substituting our values, V2 is 125 cubic centimeters times 86.175 kilopascals divided by 100 kilopascals. This gives us a final volume of 177 cubic centimeters. Well done if you got this right. Practice question 2. A gas has a density of 1.45 grams per cubic decimeter at 200 kilopascals and 127 degrees. Calculate its molar mass. Remember the formula for density in terms of molar mass and the ideal gas equation. Again, pause the video and try it out. Let's check your work for question 2. We are using the formula we derived. Our goal is to find molar mass, m, which is mass per mole. The formula we will use is m equals RRT divided by P. First, we list our variables. The density, R, is 1.45 grams per cubic decimeter. The pressure, P, is 200 kilopascals, or 200,000 pascals. The temperature, T, is 127 degrees Celsius, which is 400.15 Kelvin. R is our gas constant. Just like before, we must be careful with units. We converted the density from grams per cubic decimeter to grams per cubic meter to be consistent with our value of R. Now, we plug these values into the rearranged formula. M is 1450 times 8.31 times 415, all divided by 200,000. The calculation gives us a molar mass of 24.1 grams per mole. Another common mistake is to forget to convert density to the correct units. Practice question 3. A reaction produces 0.15 moles of CO2 gas, which is collected over water at 25 degrees. The total pressure is 750 torr. What is the partial pressure of the CO2 gas? Vapor pressure of water at 25 degrees is 23.8 torr. This question applies Dalton's law of partial pressures. Pause the video and consider the components of the total pressure. Let's analyze the solution for question 3. We use Dalton's law. The total pressure is the sum of the partial pressures. In this case, the total pressure is the sum of the partial pressure of CO2 and the partial pressure of water vapor. The problem provides the total pressure as 750 torr and the vapor pressure of water as 23.8 torr. We need to find the partial pressure of CO2. Rearranging the equation, the partial pressure of CO2 is the total pressure minus the water vapor pressure. Plugging in the numbers, we get 750 minus 23.8, which equals 726.2 torr. Notice that the number of moles of CO2 was irrelevant here. It was extra information. Practice question 4. Under what two specific conditions of temperature and pressure do real gases behave most like ideal gases? Explain why. This question tests your conceptual understanding of the limitations of the ideal gas model. Think about what allows the assumptions to be valid. Let's review the explanation for question 4. Real gases behave most like ideal gases under two conditions: high temperature and low pressure. Let's explain why. At high temperatures, the gas particles are moving very quickly. This high kinetic energy is much greater than the weak intermolecular forces between them. So these forces become negligible, fulfilling the second ideal gas assumption. At low pressures, the volume of the container is large. The gas particles are far apart. In this situation, the actual volume of the particles themselves becomes a tiny fraction of the total container volume, fulfilling the first ideal gas assumption. So, by understanding the conditions under which the two core assumptions are valid, we can explain when a real gas will approach ideal behavior. Our final practice question is a combined gas law problem. A sample of gas has an initial volume of 125 cubic centimeters at 15 degrees Celsius and 725 mmHg. If the pressure is increased to 775 mmHg and the volume is decreased to 100 cubic centimeters, what is the new temperature in degrees Celsius? This is a classic combined gas law problem. Don't forget the most important step in any gas law calculation. Pause and solve it now. Let's review the solution for the final question. We must use the combined gas law. Let's list our initial and final conditions. A crucial first step is to convert the temperatures from Celsius to Kelvin. 15 degrees C is 288.15 Kelvin. The final conditions are a pressure of 775 mmHg, a volume of 100 cm3, and we are looking for the final temperature, T2. Rearranging the combined gas law to solve for T2, We get T2 equals PV2T1 divided by P1V1. Notice that because the units for pressure and volume are the same on both sides of the equation, we do not need to convert them to pascals and cubic meters. Only the temperature units are critical. Substituting the values, T2 equals 775 times 100 times 288.5 divided by 725 times 125. This gives us a final temperature in Kelvin of 244.6 Kelvin. But the question asks for the temperature in degrees Celsius, so we must convert our answer back. 244.6. Kelvin minus 273.15 gives us approximately 28.5 dJ. An excellent job if you got the final answer in Celsius. We hope this comprehensive review of ideal gases, real gases, the gas laws, and the ideal gas equation has been helpful. Understanding these concepts is foundational for success in IB Chemistry HL. If you're looking for personalized expert tuition in IB, A-Level, or IGCSE, please contact us at DAR Tutors. Our specialist tutors can provide tailored support to help you achieve your academic goals. Thank you for watching.